So I'm going to talk about building invariant speech recognition representation for by using discriminative template learning. So basically, the motivation from the fact that, like vision signals, speech signals, you can have very different representations. Or if you look at the spectrogram, they're all the same word, but it could be pronounced by different speakers with different tempo or accent or under different contexts or with different emotion. They could look quite different, even though if they're the same word. So what we want to do is, if we want to recognize the speech or decode the speech, we want to build a representation that is invariant to those kind of transform or variants or transformations to the speech signal. Basically, what you want to do is, if you have a speech signal and you go through a transformation, you want the final representation after you do some processing to be similar or to be equal here. So the tool we use here is the invariant representation theory Tommy actually developed for the visual signals. Because it is an abstract theory here, we can directly borrow the tool here. I'm not going to talk about the details of the theory or how you compute the representation. I think some of the flash shock users will talk about that. So basically, what we do here is we take the computation recipe. You have a module that carry out the computation, and you want to you have a theory that if you do this, you will be invariant to this kind of transformations. But the question here is you will need to use templates in your computational module for simple transformation. Like for example, in vision, if the transformation is a group, you can use just random templates. It will be fine. It will be perfectly invariant. But for complicated transformations, you will need class-specific templates. We are trying to learn the optimal template that you can use in this kind of module in order to be maximum invariant and also speech selective. So the architecture we end up with is just the same as a convolutional neural network that people use extensively in vision and also in speech, except that the convolution now is convolution and pooling now is over the transformation instead of just the translation. So so basically, this is the architecture. This also serves as a way to explain basically why the convnets works very well in practice and also in visual and in speech, because it goes under the framework of invariant representation learning. So those are some results. Basically, we tried some speech classification on standard benchmark dataset, and it works pretty well, much better than the modules when you're not using this invariant representations. So that's it. Thank you.